Okay, don't forget to do your attendance checking, okay? So, yeah, let's get started. Good to see you in this Friday's lecture. So after this lecture, you have a good weekend. Yeah, and the restaurant name was thank you for it's a Friday. Yeah, okay, so let's get started. So we have been learning this sequential logic circuit. And we started from the basic introduction and latches and flip-flops. Particularly in these flip-flops, we learned the D flip-flops. Multiple flip-flops can be built for registers, right? Registers. Then with registers, what is the function of the register? The function of a register is to store data, right? It has memory. It can store multiple bits of data for the flip-flops. After that, but when we look at the flip-flop or sequential logic circuits, we realize that there are some issues in the sequential logic circuit. Then we introduced the synchronous logic design. So in the synchronous logic design, we particularly checked how we can do the logic design. Actually, we combine the combinational logic circuit and the sequential logic circuit together. For designing this kind of more complex circuit, we rely on some techniques or the design method, which are financial state machines. This is what we learned in the last lecture. So since we had our quiz in the last lecture, I'd like to review the quiz you had. Okay. So we use quiz as a way to review what we learned in the past 1 week, okay? So I believe most of you already checked your score in the RGBB. So we just check the one by one for the questions. If you have any questions in your mind, you can raise your hand and I try to answer you. Okay, the first question regarding the timing discussed in our lecture, which one has less chance to be the reason to cause the difference between the propagation and the contamination delays? So the question is ask you to find the reason that causes the differences between the propagation and contamination delays. So the correct answer is the first one, speed of the light limitation. Okay. So some students maybe get confused when you choose the answer. So the question is ask you to find the reason, that's the chance to be the reason to cause the differences. It's not the reason to cause the propagation delay. It's the reason to cause the differences between the propagation and contamination delay. Okay? So others are just, okay. Yeah, others are just the correct answer. So circuit slowed down when hot, speed up when cold. This is one of the reasons causing the propagation and the contamination delays. So do you remember, if you recall, what are propagation and contamination delays? What is the propagation delay? Anyone remember? Anyone can raise your hand to answer? What is the propagation delay? It's the minimum delay, right? The minimum delay for a circuit from the input to the output. The contamination delay is the maximum delay. So if you do the experiment or test some circuits in 1,000 times or 10,000 times, you would get some like this kind of variance, the minimum delay and maximum delay. Then it caused by the temperatures, when it's hot and cold. They can also be caused by multiple input and output. Some of the input are faster than others. Then another reason could be different rising and falling delays. Okay, the later three choices are the correct the reasons to cause these differences. The first reason is the cause to have this kind of delay, not the difference. So this is the first question. second question, regarding the glitches discussed in our lecture, which one is less accurate description for it? So similarly, this is the less accurate, means that it's not correct, right? So the first one is not correct. Glitches may happen in a circuit, but only when we implement the circuit, we can find them. So this is not less accurate description because we can use the simulation in a computer to simulate, to test first of the circuit before we implement. We make a real circuit. So if you can only find this kind of glitches when you implement, when you made a circuit, it will cost a lot, right? When you finish the implementation, the circuit is already there, but you have an error, you have glitches inside, then you need to make another one. So that's not durable. Others are just correct description for the glitches. For example, the second one, because of synchronous design conventions, glitches don't cause problem, but in real world problems, it usually happens. The third, we can remove all the glitches. It could happen. Okay, even though we tried our best to synchronize, to put all the input together, so the glitches still can happen. One way to reduce glitches happening can be using redundant gates. This is what we learned, right? In our lectures, we showed an example. So we build the circuit, but when there is temporarily falling down and rising up again, we call it a glitch. So we introduced a redundant circuit to avoid that condition happens. This is one way to reduce glitches is to introduce redundant gates, then a circuit to avoid, to block the trigger condition. Any questions? Okay. So next question. For the sequential logic circuit, which fundamental feature differentiates them from combination logic circuit? So we have been working on this sequential logic circuit. The fundamental feature for a sequential logic circuit is it has memory, right? It can store data. The first one is correct. So sequential logic circuit can store data, that is having memory. Others are just the common features that both sequential logics and combination logic have together. They are built from basic logic gates. They have delays. They may have embedded states. So if your design is not good, they may have embedded states. Any questions for this? Okay. Next one is about the D-latch. So about the D-latch, which one is a correct statement? So I gave the symbol of D-latch. Oh, yes, this is D-latch, right? So what is the correct statement for the D-latch? Then we check one by one. What is the D-latch? D-latch is that the logic is that when the clock is true, is 1, is in a high state, the Q will output D. When clock is 0, Q will maintain the current, the previous state, right? This is the logic of the D-latch. So then if you check the answers here, the first one, if clock equals low, Q holds the previous state. This is one of the function of the D-latch. Others are just not true. When clock is high, Q flips previous value. When clock is high, actually Q will get the data from D, right? Clock directly determines Q. This is not true because Q actually get the data from D, and Q is decided by both D and the clock. The last one, both input cannot be high at the same time. They can be, right? D and so we have two input, D and clock. They can be at the high at the same time, right? It's not true. So the correct answer, the correct description is the first one. Any questions for this problem? Okay, next. Okay, this one is a little bit tricky. One clock, so this is about the D flip-flop, right? So one clock equals 1, D equals 1. What is the output Q for D flip-flop? What is the fundamental function of D flip-flop? So you see here the symbol of the D flip-flop. It has the clock input has a triangle. Triangle indicating that the Q, the output, will only be changed or switched at the rising edge or falling edge. So you can consider that this triangle is like a falling edge or rising edge. Whenever you see this kind of triangle for the clock, means that the output will only be updated when there's a falling edge or rising edge. So then based on this, come back to this question. The question is asking you, the clock is 1, D is 1. What is the output Q? But the function of D flip-flop is that we need to only check the rising edge or falling edge, rising edge, right, in our lecture. So, but the problem didn't say there's a rising edge. It just says that clock equals 1. Means that it's a kind of a stable state. If clock equals 1, Q will just keep the current state, will not be switched. So the correct answer is the first one, right? Then others are just not correct. 0 or 1 unknown. So it can be 0, can be 1, but actually it's the fundamental output is maintaining the current state. Any questions?
Actually, I don't understand why it is keeping the current state while we don't know it's a falling edge or it's a rising edge.
So
just one.
Yeah, maybe that's why I say it's a little bit tricky. Since the problem here just tells you that clock equals 1. Did not say it's a rising or falling. So mostly, so if it didn't say it's a rising, so it means that it just has clock is 1 and D is 1. There's no rising edge. So it means that, the clock is 1, D is 1, Q actually just doesn't change, just maintain the current state.
So if it's a rising edge, they just tell us it's rising edge.
Yeah.
Not clock 1.
Yeah.
Okay, I understand.
Yeah. Okay. A little bit tricky, right? So, but I mean, when you look at this D flip-flop, you look at the symbol, then when you see the triangle, you need to remember that it is the output is triggered by the either rising edge or falling edge, by an edge, not by a stable state.
Just to be sure. It could be if it's a rising edge, then you can't tell what number its clock is, or then. So if it's a clock 1 right now, it could be a rising edge before, right? But not. This is not a currently rising edge, so we assume that it's a current state. Yeah, it's a current state. So if it's a rising edge, it will tell you there's a switch from 0 to 1. It's a rising edge period. If it's 1, means that it's a stable. It's already in 1. It's not just like right after from the rising edge. Yeah. Okay. So any other questions? Okay. Next. This question is about the register, right? The register is built from the multiple D flip-flops. Which statement is less accurate? So if you check one by one, the first one is less accurate because when we learn the register, inside of register, it has multiple D flip-flops. Then they need to share one clock source, right? If they don't have one clock source, then the output will be asynchronous. If the output is asynchronous, then
The thing is, it's just lost the meaning of the register. The original function of the register is to store the data and synchronize the output together, right? So the first one is less accurate. So they need to have a same clock source, okay? Then others are just true. A register can be built from unparallelized D flip-flops to store n-bit data. So the number of D flip-flops decides the n-bit data. The purpose of using registers inside CPUs mainly is for storing data and quick processing. This is what we shared in our lecture, right? When we talked about these registers, what is the use of a register in the CPU? So actually we are using it for the storing data and the quick access for the arithmetic logic function. The last one is what we are just explaining. Registers used in CPU have multiple types to serve for different purposes: instruction register, data registers. So the CPU access the internal function component in the CPU access the data inside of the register to do the calculation, to do the arithmetic calculation. Okay. Any questions for this problem? Okay. So next one is about the resetable flip-flop. Which statement is correct? Okay, yeah, when I checked your answers for this question, yeah, most of students got wrong. So I don't know why, but actually if you read through, actually the correct answer is obvious. So firstly, so it's a resetable flip-flop, right? What is a resetable flip-flop? Reset. What is a resetable flip-flop? When you put the reset equals 1, what happens? Anyone?
Force the Q to 0.
Sorry?
Force the Q becoming a 0.
Yes. So it's like reset, right? If you put reset equals 1, forcibly make the output Q to be the 0. So with this in mind, if you remember the function of this resetable flip-flop, then we check modification of the internal circuit is required for asynchronously resetable. So this is what we shared, right? When we learn this resetable flip-flop, it introduced the synchronous and asynchronous concept. Naturally, resetable flip-flop is synchronous design. If we want to make it asynchronous, we need to change the internal circuit, modify the internal circuit of it. Then others are just not correct. The second one, if you put the reset equals 1, so as you remember, if you put the reset equals 1, it actually forcibly put the output Q to be 0. But here it just says that behavior like ordinary D flip-flop, which is not the correct answer, right? Actually, you need to force the output Q to be 0. Given that said, so if you read just the first part of this sentence, you know it's wrong, because it's a resetable flip-flop. There's no set input. There's only reset input. Okay, this is wrong. There's no set input. The last one, modification, so it's just the last option, the choice is just exact opposite of the first one, which is true. The internal circuit, so actually we don't need, right? Oh, there's a, okay. I guess there's a mistype here, right? Modification of internal is required for the synchronous resetable flip-flop. Okay, there's a missing is not, I guess. So that's why most students got it wrong. Actually, there's missing is not required. Okay. So yeah, then I guess every one of you got the extra points for this question. So yeah, so this is, you have any questions for this problem? So the thing is there's a missing, is not required. There's one missing, one not, okay? It's not required for the synchronously resetable flip-flop. Okay, next question. For synchronous sequential logic circuit, which statement is less accurate? So when we talked about the synchronous sequential logic design, we particularly checked the issues we had in the sequential logic, right? Those issues are oscillating and race conditions. That's why we try to combine combination logic and sequential logic together to avoid these oscillating and race conditions. So this is less accurate because we try to actually, the purpose of this is to avoid, but it says they cannot avoid oscillating and race condition. The thing is that when you use this, actually we try to avoid oscillating and race conditions. And others are just the definition of this synchronous sequential logic circuit design. They break the cyclic path by inserting registers. So you remember, if there's a cyclic path, and we put the registers to synchronize it. Every cyclic path in them contains at least one register. So there's at least one to synchronize the signal. They integrate combination logic and the sequential logic circuit together. This is the purpose. Okay? So yeah, this is all the questions for the quiz we had. Any questions for the last problem? Okay, so let's move on. So in the last lecture, we have been learning the design procedure by using FSM, right? The FSM design procedure. We checked from the step 1 until step 8 by an, sorry?
Recording is not on.
Thank you for reminding me. Okay. So I will record again for the quiz. Yeah. So FSM design procedure. So we have been learning this FSM design procedure. It starts from step 1 until step 8. So we checked one by one, right? We use this traffic light controller as an example to show how we can follow those steps to design a synchronous sequential control logic for this traffic light controller problem. So for this problem setting, we have these two sets of sensors, T and TB. It will detect the traffic. If there is a traffic, then it will affect the traffic light to be switched or not to be switched. So we have the input traffic sensor, TA, TB, the light, RA, RB, traffic light, RA and RB. Then there's a clock source. Every 5 seconds, there's a rising edge. Then at time, it will check whether we want to change the traffic light. So for this problem, we went through from the step 1. We first identify input and output. Input are clock, reset, TA, and TB. Output are RA and RB. Then the initial state is in this academia road is green, bravado road is red. Okay, this is the initial state. Now based on those kind of logic, we first build our state transition diagram. State transition diagram, we start from the initial state, which is S0. We use S0 to represent this is the initial state. So particularly when you design state transition diagram, you put a circle. Inside of circle is the state number. Then the other information are the output. Okay? For example, here RA and RB are the output for this state. Then transition data, information, or conditions are the input. They will be tagged in the arcs or arrows. So if we just check this kind of logic in this traffic light controller, we started from S0, moved to them based on the input TA and the input of TA, whether it's true or false, and we decide whether we maintain the current state or move to the next state. The next state is that the output will be RA is yellow, becomes yellow. Then from the S1, after 5 seconds of the period of the time, then move to the S2, switch the LA to red, and switch LB to green. Similarly to for the S2 state is similar to the S0 state. So it will just check the input of TB. We just check the input of TB, whether TB is true or false. If it's true, means there's a traffic. If it's false, means that it doesn't have traffic. If it's false, if there's no traffic anymore, we don't need to maintain the green output for the LB, the traffic light. Then you move to the state 3, S3, and switch the LB to yellow. Then after 5 seconds, then you will switch to the state 3 will switch back to the initial state, which will switch LA to be green, LB to be red. So this is a state transition diagram we built based on this problem setting. So now next step is to build the state transition table. From this state transition diagram, we can directly build this transition table, right? You have current state, you have input, then you can write down the next state. So since S0 has 2 outgoing arcs here, then we need to put 2 S0 states here because it has 2 next states. It could be itself, it could be S1. So you can just write down, fill all the next state one by one. After filling it, you will see it just follows this state transition diagram. Next, we need to do the encoding, right? Since the digital circuit only can deal with 0 and 1 binary data, then for this state we designed, the state transition diagram, it has 4 states. We need to use binary data to represent the 4 states. Then for that case, we need to use at least 2 bits, right, to represent 4 states. With this is the binary encoding. With this binary encoding, we just replace the previous original state from S0 to S3, and next state also similarly we encode it by the binary encoding. Then we fill out this next state. So after building this encoded state transition table, we can directly get our logic, the Boolean equations, right? So by observing the next state, this is the next state, right? S1 prime, S0 prime. S1 prime, we use the minterm for this column. Then by observing it, we realize that it is actually a XNOR logic. We put S1, XNOR, S0. For S0 prime, we get the minterm when the output is true, which are from this row and this row. And we put 2 terms and we add them together. So this is how you can build the Boolean equations from the encoded state transition table. Next step is to build the output table. The output table is generate the traffic lights output to control signal for the traffic signal, right? Whether the traffic signal need to be green, yellow, or red. Since we only have 3 output, we also need 2 bits as encoding, right? But we only use 3 of them, 0, 0, 1, 1, 0, to represent the 3 outputs. With this encoded information, we put them one by one into this output table. So previously we just have LA green. Now this time if LA is green, we need to use 0 and 0. Similarly others, we can just fill it based on the previous output and with this encoding. After this encoded output table construction, we can easily get the Boolean equations. This is for the output logic for control the traffic lights. Okay, next. Now, so far we have just built all the conditions, all the information we need. With the Boolean equations, we can draw the schematics, right? Circuit schematic. We start from the state register, because state register should be the center of your digital circuit. It kind of synchronizes your signal, your data. You have input, which serves the next state you're gonna use. The current state, S1, S0 is the current state. So every time there's the next state will be synchronized through this register. Then for the next state logic, we already built the Boolean equation. From the Boolean equation, you can easily get this circuit. Next state logic, which receive two sensors input from TA and TB. So remember that this is a combinational logic circuit, right? There's no kind of a synchronization. So whenever you have a change, you have an update to this circuit, you will have some, after having some propagation delay, those data will be reflected to the S prime. Let's say immediately. Even if it has a very short delay, but it's kind of, once you have some update TA and TB S1, S0, it will be reflected to the S prime state immediately, right? Because it doesn't need to wait the clock rising edge. Keep it in mind because it's important to check the timing diagram. Then for the output circuit, the output logic is to control the traffic light, right? So because we already encoded the traffic light, the RA and RB, then from these Boolean equations, it's easy to get the circuit schematic. Then similarly, this is also combinational logic. Whenever you have a new state output from the state transistors, then the output will be reflected almost immediately, even though with the propagation delay. So also keep this in mind then when we check the timing diagram. So in this way, we just build our schematic. We followed the step from step 1 until step 8 by the Moore FSM, right? So we have you have the state register, and left hand side is the next state logic, the right hand side is output logic. Last lecture, we were checking this timing diagram. So I don't know, after the class, did you check this timing diagram? Did you have any questions for this timing diagram? Which part you don't understand? So in the last lecture, I mentioned that every cycle is 5 seconds. Cycle number 1 until cycle number 10. It's a 5-second cycle, the period, right? So let's just check one by one. So let's check it again. Last time we just roughly checked. If you look at here, you have a reset. You look at the state transition diagram. You have a reset, then you will force the state transistors, state register to be 0, right? To go to the S0. So it will immediately affect the state register. So once the state register receive this reset, then it will cause the RA and RB. If you look at here, when you put the reset to 1, S0, S1 will be 0, right? Will become 0. Then it will immediately affect the output of the traffic light control. So RA and RB, from this diagram, you will see it will be switched to green and red. Whatever previous state they are, it will just switch to green and red. And at the same time, look back here, since this S0, S1 also will be the feedback to the input, it will also affect the next state, right? The current state is a feedback to the input, to here and here, along with T and TB. So it will also immediately affect S prime in the next state, right? Because there's no register. This is a combinational logic circuit. The change of input will immediately shown in these two nodes. So which is shown here, the S prime will be immediately shown an update. Okay, so now actually S prime is the state will be synchronized through the register. So from now on, we need to check the TA and TB. TA, TB are the sensors. If it's true, means it has traffic. If it's false, means that it doesn't have traffic. So TA is at this. If you look at here at this moment, is 1, right? Means there's a traffic, there's some pedestrian walking by, then we just need to maintain the current, the state, S0. So S0 will not be changed. Until reach to this point, there's a input change. TA is switched from 1 to 0, then will immediately affect the S prime. So S prime is switched to S1. The previous was the S prime, right? Now it's a S1 state from S0 to S1, affected by the sensor TA. So this S1, the next state, hasn't been affected to affect the current state. So this S prime state will be stored in the register from this time point until the next rising clock. So from this time point to the next rising clock, the S1 state will be saved in the state register. When we reach to the cycle number 5, there's a rising edge. This S1 will be outputted by this state register, right? From S1 to S prime to S, right? Now, since now the current state is S1, so it will immediately affect the output, right? The output is check the output logic. You will immediately check S0, S1, then update the control logic. In this case, it will update LA to be yellow. LB still be the red. So the LA will become yellow, and so the LB is still red, did not change. Also, it will affect the next state, S prime, to change, because similarly, the current state will be fed back to the input and immediately affect the next state. So then S2 will trigger the next state to be S2. So this S2 from this time to the next cycle number 6, so S2 will be saved, stored in the register, and that rising edge will be reflected at S2. Okay? So then the remaining is similar. You can just check once S2 is in the output, it will just directly trigger the output control signal for the traffic light. Then trigger LA and LB to be red and green respectively. Yeah. And you can just continue check the next update is caused by the TB. Because at this moment, the LB is green. We only need to check whether TB is true or false. TB from this point is kind of falling down from true to false. Then trigger the next state to be switched to the S3. Then after the 5 seconds, reach to this rising edge, then it will be outputted to affect the final control output for the traffic light. So this is the timing diagram for this FSM example for controlling the traffic light. So any questions for this process? So yeah, so midterm will cover until this point. Okay. And yeah, so this is a very important part for this course. Actually, this synchronous sequential logic design, logic circuit, is a combination of all the knowledge we have been learned so far. Number system, Boolean equations, the combinational logic, and sequential logic, all we put them together. Then we can build very complex digital circuit. They are useful for designing the real-world problems. So yeah, since we have this example, let me ask a question. So we are designing this digital circuit we use the hardware, right? We have this design, we have this whole design. You need to use some hardwares, those devices, to build this kind of circuits. What is the difference between this kind of hardware design with the software design? Obviously, you can design some logic controlling process by the software, right? By the C++, or Java, Python, any general programming language. You can use that. Then what's the difference between this electronic design and the software design? Anyone? Just you can share any thought you had for this. Yeah. So I mean, so far we have been learning this. I mean, the topic is a digital design, digital circuit, right? We are designing digital circuit. Then actually, for those most of the functions, we can use the software to implement, to realize that. But why do we get bothered to design this kind of circuit if we can use software to implement it? What's the difference? Any possible differences you can share? Anyone? Okay, so from my side, one possible difference is that when we design this kind of digital circuit, if you implement it with some hardware, for example, I don't know if you know the FPGA. With the FPGA, you can implement this kind of circuit without using extra. It's the kind of put all those logic gates inside of the FPGA as like a CPU-like device. Once you put this design, actually the circuit is fixed. It's dedicated for this purpose, right? It's a kind of special purposed circuit. But when you use the software program, you write some code to implement this logic and output some control signal to control the traffic light. If you consider that all those software programs actually is compiled into the machine readable code, right? Assembly code or machine code into the CPU. Actually, the CPU will calculate those logic, those process for you and generate some control signal, I/O signal to some sensors or controllers. So those processes actually, the CPU is a general purpose digital circuit, right? So we can put any program to be run in the CPU. But here we are designing a special purpose digital circuit for a particular function. This is one difference. Any other thinking? Any other thought? Mm-hmm.
I have a question before this.
Okay.
Is it really like individual thing that electronical design and software design? I think it's electronical design is built upon, software design is built upon the electronical design. Yeah, that's partially true, because when we are learning those kind of special purpose design for digital circuit, later on if we can just kind of generalize different kind of arithmetic operations, like adder or multiplexers, those kind of information, those devices together, then we actually can build the general purpose of CPU. So in that case, those softwares are translated or combined into the hardware languages, to fulfill the purpose. Yeah. But in some scenarios, okay, it's actually there's another difference is here. If you build a special purpose digital circuit, actually it's faster than the software, because the execution speed only depends on the physical limitations, the speed of light, right? Once you have this, it will kind of very short to reflect the update. But if you build the software, the kind of they may have go through internal those kind of the calculation process, then it kind of delay, a little bit delay, higher delay. But one good thing for the software design is that it's flexible.
When you have a new thought, new thinking, new model, then you can easily update the model, right? You can just rewrite, add a new module inside of the software, and you have new functions. You can easily to upgrade to the next level. But for the digital design, once you build a digital circuit, then it's fixed. Later on, if you want to upgrade the digital circuit, you need to rebuild, redesign a new digital circuit to fulfill some new purposes, new functions. Okay. So yeah, this is the purpose of the comparison between the digital design, or electronic design, and software design. Okay, in the last lecture, we also checked this binary encoding and one-hot encoding. So far, we just used this binary encoding. Binary encoding is that when you have k state, it needs log 2 k bits of state, right, to represent the k state. For example, here, if you have 4 state, you need to use 2 bits of state to represent the k state, for this case, 4 states. We can also use a hot encoding, one-hot encoding, which is that only one state bit high at once. So we call it each bit of this one hot encoding is one state bit. Okay, at each time, just one state bit is high, is true, other state is false. For example, if you have 4 states, we need to use 4 bits to represent it, and only one state bit is high each time. In this case, since we have 4 input, 4 states, or 4 bits of data need to be saved, need to be kept during the circuit, right? Logic design. So we need to use more flip-flops. We need to use larger the registers, right? So it requires more flip-flops. But at the same time, the input logic and output logic will become simpler. So let's take a look at the example. So we are checking this example, a divide by n counter. What is the divide by n counter? The output is high for 1 clock cycle out of every n. So for example here, for this timing diagram, if you look at here, the divide by 3 counter, you see, from the timing diagram, you can directly see the difference, right? Every 3 cycles, then output true. 1 cycle, second, third, and 3 cycle. Every 3 cycles, and output 1. So it's called divided by, in this case, 3 counter. Then it's a simple, very simple logic, right? You can, if you have a clock, then you can easily generate some divided clock cells. In this case, we can build the state transition diagram. Since this example, we started from output equals 1, y equals 1, then we just started from this state, S0, y, the output y equals 1. There's no input, because the only input is clock itself. The clock triggers the state transition. There's no input. So there's no information on top of the arrows, arcs, right? So then it just switch from S0 to S1, S1 to S2, S2, because since we already have the 3 period, then it output y equals 1. So very simple state transition diagram. And with this state transition diagram, we can build the state transition table and output table together. It's simple, right? Current state, next state, S0, and the next state is S1, S0, S1, S2, S0. One by one, we can write down here. And output table, so you need to check the information inside of a circle. The output table, so only when we are in S0, the output is 1. In other state, the output is 0, which fulfills the every 3 cycles, the output is 1, right? So we just built this state transition table and output table. Now we need to do, what is the next step? Encoding, right? So we have these 3 states. So we cannot just use, if we just have 2 states, we can just use 0, 1 to represent. But we have 3 states we need to encode. we use since we are checking the one-hot encoding and binary encoding. So particularly we check, if we use one-hot encoding, it would be look like in this way, 0, 0, 1. So each state bit is 1. S01, S number 0 subscript is 1. S number 1 subscript is 1. S number 2 subscript is 1. So in this case, then if we use the binary encoding, then we just use the binary number from 0, assign it one by one. So since we are checking both one-hot encoding and binary encoding together, right? So next. So once you have encoding, then we can update the state transition table and output table. So in this case, for the binary encoding, the state transition table, we can just update it easily. For the one-hot encoding, a little bit different, okay? If you look at here. So in the binary encoding, from the encoded state transition table, we can easily write down the Boolean equations. For example here, S1 prime equals, we just use the min term, which is S1 bar, S0 bar, and put to here, right? Similarly to S0 prime. And then Y is also, actually we didn't put this output table here. Output table, if you look at here, the output only S0 is 1. So this Y is equals 1 is the S0 when both are the S0 state. S1 bar, S0 bar. But for one-hot encoding, it's a little bit different. Since we are using one-hot encoding, so each state guarantees that only one state bit is 1. So we can directly use that, for example here, S2 prime, the 1, when it's equals true, then we can just directly use the state bit to represent its output. We just use the S1 to be here. Instead of previous, if you follow the binary encoding, you need to use all the state, right? S2 bar, S1, S0 bar. But in one-hot encoding, we just need to use S1, the state bit. Similarly to others, S1 prime equals S0. S1 prime, which is here, and is the corresponding state bit, which is S0. Similarly, S0 prime is S2. Then output Y equals S0, which is also from here. The output when the state is S0, then as number 0 subscript is true, then which should be the output. Okay. This is the one difference between the one-hot encoding and the binary encoding to generate the Boolean equations. Any questions for this point? Okay, let's move to next step. So yeah, once you have those Boolean equations, it's easier to build schematic, the circuit schematic. You have, you always start from the registers, state registers. You have 2 inputs, right? Then you have the next state logic, which will output S prime. Then they are from the source of S0, S1. You can also have the output from the current state S1, S0, which are using this AND gate with inverted input. So you can just directly build this digital circuit. If you use one-hot encoding, the style also kind of different. So based on these Boolean equations, if you look at here, actually if you start from the first equation, so S1 is the current output for the S2 prime. So we put the S1 here. S1 will be the S2 prime's output, right? Yeah, put to here. Then let me write down. So it's different from the binary encoding. So we have the one-hot encoding. So S1, so you start from the first equation, you have a S1 here. Then S1 is equals to S2 prime. Actually, S2 prime is here, right? S2 prime. This is how you can build the schematic, right? Based on this equation. So it's kind of different from the previous one because there's no combinational logic for the next state and the output logic. There's only registers. 3 registers with serializer together. So you have the first one, S1. We use the first the register, output S1, then link to the input of the S2, which is the next state of S2. Then S2 will be the S0 prime, right? So S2 prime output S2. Then from here, S0 equals S1 prime. Actually, it will come back to here, S1 prime, right? Then S1, you have a S1, then you write down 1 register, the output, and it will forward the information, the input data to the second register, which is S2 prime. S2 prime will generate the S2, then S2 will be the third here, S2, then you draw another register, which is S0, S0 prime, then output S0. S0 is feedback to the, which is here, right? S0, you feedback to the S1 prime. In this case, you just write, you draw 3 registers. Then the output Y is just directly S0 from this Boolean equation, right? So a little bit different from the binary coding. Any questions for this, the one-hot encoding circuit schematic? Mm-hmm.
Last
Yeah.
is Y set.
Yes.
S. Why not reset?
Oh, reset here, right? You mean the reset? So Y actually based on the Boolean equation, Y equals S0. So the S0 will be the output to Y. So because this last one is S0, it's directly output to Y.
Why use settable in last?
Settable?
Register is S mean not settable. Another is
You mean S. Okay, a good question. So yeah, so you may notice that the first 2 we use the reset. This one we use the set. It means that actually we can set the output to be 1 intentionally, which follows the design of here, the initial. So even though here we use the reset, it can also be the set to 1, the output to 1. So we set, since this timing diagram we are setting is from 0 to 1. That's why the last of this register, we use settable registers, right? Then we can, when the initial state, we can set the output to 1 and continues the timing diagram. That's from the design of here. I mean, it can also be, since this timing diagram started from the Y equals 1, it can also be started from Y equals 0. In that case, then you can switch actually the position, but the logic is actually the same. You can put the reset to be here and the set to be here. So the logic is the same. It depends on the timing, the state transition diagram you built. The Y output can be in the middle, S1, or can be S2. Depends on this timing diagram you are setting. You can put, for example, you start from in the middle from somewhere here, and after 3 o'clock, then you start from 0. So it means that you will start the initial state from S1, then reach to the S0. Depends on the sequence. Okay? Any other questions? Okay, so let's move on. So yeah, a good question. So you observed carefully, you notice that they are different, right? You have two resetable register, one settable register. Okay. So when you deal with this kind of issue, maybe this is not actually the key or some like decisive factor to generate the correct circuit. So you can, based on the previous design, you can generate this kind of circuit. It can also be another design, as long as the logic is right from the beginning. Okay, so now we move to another topic. So far, we have been checking this Moore FSM, the design procedure following the Moore FSM. Actually, we have also another design principle called mini FSM. The difference is that the mini FSM output logic received both the current state and the input. Okay, the output logic will be decided by both the current state and the input. The input could be the sensor information or clock, any other information. So in the previous case, the input is the sensor, right? The traffic sensor. But for the Moore, the output logic will only be determined by the current state. So actually both techniques, both principles are correct. We can design them together. So let's take a look at the example, how we can use the mini FSM to design the digital circuit. So you remember, this is, you recall the design procedure. We have been going through this step 1 until step 8. So now we are particularly checking this step 6. For mini machine, actually we need to rewrite combined state transition and output table. Previously for Moore machine, we first rewrite state transition table with encoding and write output table. But for the mini machine, we need to do them together. But both techniques are right, the correct design. For example, we have this kind of silly example. So this guy has a snare, and this snare has kind of crawled down a paper tape, and with 1 or 0, 1, 0, 0, 1. And the snare smiles whenever the last 2 digits is 0, 1. It's like kind of detector, whether the digit is 0, 1, is last 2 digits. If it detects, it smiles. Then we can, this very simple, right? So you, for example, you have this kind of 0, 1, 0, 0, 1, 1, 0, 1, 1, 1. Then this, you can consider it as a robot. And it has some sensor, scan sensor or camera sensor, any sensor. Then walk by, cross over, then detecting some particular image on the ground. Then whenever it's identified some pattern, then it will generate some output. In this case, it smiles. It can also be, if it's a robot, it can be some light or any signal. So to model this kind of problem, we are going to use both Moore and mini FSM to build it. So we have this, the input and the output. The input A is a snare's antenna, is a detector. So it's each step, it will detect 1-digit number. The output is whether true, means that it will smile. If false, it doesn't smile. The sequence, the sample sequence is in this shape. So the thing is that, so for this particular problem, how we can use both Moore and mini FSM to design it. So the first thing is get the input and output, we already did. Then draw the state transition the diagram, right? State transition. For more FSM, so you can get this state transition diagram. So the thing is, so we have a state circle, then state inside of circle has output, transition, there's arcs, have input. So this is from the more FSM. But for the mini FSM, inside of the circle, it doesn't have output anymore. Then we put output into the arcs. So we use the slash to separate input and output. The slash to separate input and output for this mini FSM state transition diagram. So how we can build this kind of state transition diagram generally, our purpose is to detect the 0-1 pattern, right? For example, you have this the sequence, the number sequence. So whenever you see a 0, you need to decide whether the next digit is 0 or 1. If it is 0, then we just keep the current state. If it is 1, then we successfully detect it. If the current state is 1, we need to detect the next state is, because, if the current state is 1, whatever next state it is, it will not generate the pattern 0-1, right? So we just continue until we find 0. So this is the logic we built this transition diagram. For example, here, so this is more FSM. Inside of a circle, it is the output. The output, which from the number. This is the output. Yeah. Oh, sorry. The output. So this is output is for the whether it's smile or not smile, right? The input is on the arc. So for this state S0, starting from the original state, it did not smile. It's in the fourth state, the output. So now we just need to check the next state. The next input is 0 or 1, right? So for example, this robot, move toward to the first digit, then you realize it's 0. Then what is the next state for 0? Because it just follows the pattern, the 0-1 pattern we are searching for, right? So it would need to move to the next state to decide when we move to the next digit whether it is 1 or 0. So the output for the S1 is still 0 because we haven't decided whether we are in the correct pattern. We got the correct pattern yet. So once you reach to the 1, so the next input, which is 1, so this snare just successfully detected, oh, we have 0, 1, this is the pattern we are looking for. Then it will smile, generate a true output. So after the first 2 digits, the next one, it could be 0, could be 1, but it doesn't matter, right? Because since our pattern started from 0, if you start the current number is 1, whatever next digit it is, it doesn't change the detection pattern. So our current input is 1, then the two outputs will be either 0 or 1. If it's 0, then we need to start from, because 0 is the possible pattern we are looking for, right? We need to check whether the next state input is 1 or not. Otherwise, if it's 1, it's just not the pattern we are looking for. We need to switch back to the initial state, starting from the beginning to detect. If it is still 1, the next bit input is still 1, yes, that is not following the pattern. We just keep circling around by itself until we find the pattern 0. Once you have a 0, you need to check the next input. So this is how you can build the state transition diagram for the more FSM. On the other hand, for this mini FSM, it just has 2 states, S0 and S1. Then the output is on the arcs, right? So from S0, it has 2 inputs, whether it's 1 or 0, right? It's similar to the 0 and 1, but in this case, it's actually along with the output. Output will be attached to the state transition. So if it's 1 and the output is 0, if it's 0, the output is still 0, and you move to the S1. Similarly, we detect. Since we have a 1 input, now we need to detect whether it's the next bit is input is 1 or 0. If it's 0, then just circling by itself. If it's 1, then we successfully detect it. Then output is 1. So the state transition diagram for the mini FSM is simpler than the more FSM. Actually, we can just go through those state transition table. So once you use the staging, this transition diagram, you can build the table, right? From the current state, the next state, with the binary coding. Then you can just feed out the binary coding, the current state to the next state. Then with this state transition table, you got the Boolean equations. With the Boolean equations, you can build the digit. This is output table. So remember that for the mini FSM, the output table will be built together with the state transition table. So we just easily to get the output y equals S1, which is in this, right? Okay. Next, now we use mini FSM. We need to build the state transition and output table together. We use this 0, 1. Since we only have 2 state, we just use 1 bit encoding is enough, 0, 1 to represent. We just write down this input and output, right? So remember the first, before the slash is input, after the slash is output. Then you can just fill the output to here. The next state is from 0 to 1, for example here. S0 has 2 outgoing arcs, then the next state will be either itself or S1 will be either 0 or 1. So it depends on the input. So if it's input 1, then it will be 0. If input is A, if 0, then it will be 1. So in this style, you can fill it out, right? If 0, if the input is 1, which is here, right? The input is 1, then it will come back to itself as 0. If input is 0, it will go to the S1, which is 1. At the same time, the output, the only output we are seeing is located here. From S1 to S0. From S1 to S0, then output is 1. So in this way, actually, we just built this. We built the state transition table and state transition and output table together. So once we have this table together, then we can write down the Boolean equation. So this is the schematic from the Boolean equation we have built. This is the mini FSM schematic from the table we just built. So you see here, mini FSM, the output, the combination logic of the output circuit receives the input directly from the next state logic, A here, right? A will directly affect the final output. So this is the design of mini FSM. Any questions for this mini FSM? So both methods are okay to use. There's just different design principle. Both designs are correct. You can either use more FSM or mini FSM. There's no wrong. It's just design principle. So if you look at here, maybe sometimes mini FSM is a bit simpler. I mean, from the schematic point of view, it's simpler, the digital circuit point of view. But for the more FSM, it's a bit complicated. So the complicated part is the state register. You need to use 2-bit state register, right? But here it's only use 1 bit. Means that 1 flip-flop is enough. Okay? Do you have any questions about this mini FSM? Okay, so let's take a look at this, the timing diagram. So you probably will see this timing diagram a lot, because when the digital circuit become much complex, then this timing diagram also will become very complex. Assuming that you have, currently we just check like 2, 3, or 4 states. You have this kind of state switching. Assuming that you have like, let's say 16, 32 state. Then your state switching will starting from S0 to a lot of states more to switch, right? Actually, this is what's happening in the CPU. So you kind of switch into different states. So just simply check what's going on here with Moore and mini timing diagram. So we have this. This is Moore machine. It's a mini machine. Moore machine has 3 states, right? S0, 1, 2. And the Moore machine has 3 states. Mini machine has 2 states, S0 and S1. So their output decides by the A, right? So it detects the pattern 0, 1. Whenever there's 0, 1, it will just generate the output. So for example, here you have this reset. Let me check the, reset. Once you are resetting, so it immediately affects the machines, the digital circuit you designed S0. They will switch to the initial state, okay, to the S0. Now it just goes by, then so this sequence, this order, the number it detects, start from A, it detects there's a 0 at this moment. Actually, it doesn't affect the change for the state transition, right? So then only when this state affects the S1, the output of the state at this rising edge of next clock, then switch to S1. Both machines will switch to S1. The next check, at this moment, the A become 1. Oh, this is the pattern we just did. The state also need to switch. They will trigger both machines to switch to a new state in the next cycle, S2 and S0. So in this case, so they will output 1, right? Output 1. So you would see that the mini machine output 1 at this moment. The Moore machine output 1 at least after the cycle 4. Because the mini machine is affected by the input A, right? Once you have since here, once input A has some shift, actually direct affect the output Y. But on the other hand, this Moore FSM will only affected by the current state. So the input state will be delayed through this register and affect the output Y. So you will see here the output Y will immediately reflected this issue because it detected the 0-1 pattern and generate the true output. So we can see that mini machine is more sensitive or immediately reflect the input, right? But the Moore machine, the output is delayed until the next rising edge because the state is going through the register. So then we just continue to check. So in this case, 0, so the input is become 0, and then they just switch their state. So from this 0, back to the S1. So if you look at the timing diagram or transition diagram, you will see, state transition diagram, you will see, if you add this input, then you would switch to the next state, which is S1, in the middle, right? And you can continuously check all those kind of logic. So any questions for this both Moore machine, both Moore and mini timing diagram? Okay. So yeah, I guess the time is reached. And yeah, we stop here, and we stop our lecture here, and we will continue our lecture after the midterm exam. So our midterm exam is next Tuesday afternoon, 3 p.m. to 4 p.m. in this room, okay? And the scope will cover until here, before the state encoding, before this timing diagram, okay? The scope, until this 52 page of the slide. Okay, any questions? And if you want to check your quiz answers and the questions, you can visit me or TA. I will share your answers with TA. It will be more flexible for you to visit TA to get to check your answers. Or you can visit me on Monday afternoon's office hour. Okay. Thank you for your attention. So you need to do the survey. So let me show you the This is for English. So right hand side is English, left hand side is in Korean. Yeah, you can scan it and do the survey and submit. Yeah, this is English, the other side is Korean. So if you finish the survey, yeah, we are done today. See you in Tuesday's midterm exam. Okay? Have a good weekend.